Hello class, today we are going to spend some time focusing on states of matter, particularly the solid and liquid state. We just wrapped up a whole unit on the interactions of particles in the gas phase, or lack thereof. We know that things in the gas phase tend to have very little interaction with each other, and that's when it's considered ideal. When they do start to have interaction with each other, that's when we start to view them as real gases. Certainly some things we'll continue to talk about today, but we're focusing on the liquid and the solid state, where we need to understand the different types of solids and their structure. We need to understand the effect of vapor pressure on the liquid and gas phase, and then lead into a discussion of change of state and phase diagrams. And all of these things are going to be framed by looking at the intermolecular forces between the molecules. So a quick comparison of the intermolecular forces, here abbreviated as IMF, by the different states. In a solid, the IMFs tend to be very strong. These are ion dipole forces, which we'll discuss in a later play posit. The ion dipole forces, or even dipole forces, depending on the solid type. These are all very strong interactions that result in minimal motion. That's why our solids tend to be static. They don't move very well. There's not a lot of molecular vibration going on. When we get to the liquid phase, there's quite a bit more motion. They tend to flow a bit more. The intermolecular forces can still be strong, so they still have some decently high boiling points and melting points, but not as strong as the solid state. When we get to the gas phase, we have very little interaction. The collisions are elastic, therefore when they collide, they don't have enough time in proximity to each other when they bump in to actually form these intermolecular attractions. And there's a lot of force behind those collisions as well, so they just bump into each other and bounce off, and they don't have the ability to really form those intermolecular forces, since it makes a lot of sense as to why we view them as ideal. We don't have to worry about these extra interactions happening. In the liquid state, we're going to look at a lot of different physical properties, including surface tension, capillary action, and viscosity. We will continue looking at these more in depth, but this slide has a good rundown of what they are and why we care about them. Surface tension is a resistance to an increase in surface area. So if we have a high surface tension, we have strong intermolecular forces, which means it's hard to disrupt the interactions between the molecules at the surface of the liquid. So the molecules on the surface only have an attraction to the molecules below it, and the strength of those intermolecular forces with the molecules below increase the surface tension. And so when we have a high surface tension, it's harder for water particles, or water is just an example, it's harder for particles to escape the surface of our liquid, which relates to our vapor pressure. When we're looking at capillary action, that's the ability of a liquid to rise in a narrow tube. There are adhesive forces between the molecule and the glass. Glass is silicon dioxide, and we'll talk about that a little bit later as well. And that has its own unique intermolecular forces. So capillary action is the interaction between the molecule and the glass particles, and those adhesive forces can overcome the cohesive forces between the molecules, and it causes it to literally climb up the molecule, or up the glass tube. If you've ever used a capillary tube before in biology, or any sort of biology lab, that's where you would typically see capillary action in place. We also have viscosity, which is a resistance to flow. Think things like maple syrup. It does not flow very well unless you increase the temperature, which we'll talk about later. Those things tend to have strong intermolecular forces, and viscosity increases as the molecule becomes more complex. We'll talk about that as well. With types of solids, we have amorphous solids, which have a lot of disorder in their structure. It's not a straightforward bonding method. Things like glass can be considered amorphous solids. It's crystalline. It has a very regular arrangement. of their components, and you'll see it's very nice and neat. Sometimes we call it a lattice structure. The liquid states, so viscosity, they all vary in viscosity. The thicker the liquid, the more viscous it is, which means we have stronger intermolecular forces. Something that impacts our viscosity is our size. If we are larger in size, we have more electrons. And so since we have more electrons, we are considered more polarizable. And that'll be covered in another play posit as well. So if we look comparing just hexane to decane, decane has a lot more carbons and a lot more hydrogens. And so therefore it is more polarizable because there are a lot more electrons as a result. Since it is more polarizable, it will have a very strong London dispersion force. In this case, these are both, comparing hexane and decane, they're both nonpolar substances. Since they have large London dispersion forces, it increases their viscosity. However, as I stated a minute ago, as the temperature increases, viscosity decreases. Reasoning behind this, if we look at increased temperature, we're increasing the average kinetic energy of our particles. When we increase the average kinetic energy of our particles, there are more vibrations occurring between the molecules. When there are more vibrations occurring, it can disrupt the London dispersion forces that are occurring between our particles. And therefore viscosity must go down. When we're looking at surface tension, like I said, the molecules are only interacting and forming intermolecular forces with the molecules below it. So we're looking at specifically the surface molecules. If you have a strong intermolecular force, the greater the surface tension as a result of interacting with the particles below. This picture is great here because this shows the interaction with the particles below, whereas when we get underneath the surface, we have interaction with everyone around us. So surface tension specifically describes this phenomena here. If you've ever looked at surface tension, this is the classic lab in biology is you try to get the paper clip to float on the surface of the water. That's because the intermolecular forces and the surface tension of the water is greater than that of the attraction for the paperclip, and so the paperclip can float. Some spiders can also walk on water as a result of this because their surface area does not disrupt the surface tension of the water. So some fun facts, and this you don't necessarily need to know, but if you want to take a look at some of this, it is very interesting and a good real-world application. The reason we use soap is because soap particles can reduce the surface tension. It doesn't actually kill the germs, it just surrounds them in what we call micelles. Micelles are your soap suds. It's the fatty acid chains that are in the soap, and so the soap breaks the oil into smaller drops, and then it can mix into the water more efficiently. It works so well because we have the hydrophilic head of the soap molecules, because they're basically just a bunch of fats, and those can form strong intermolecular forces such as dipole-dipole with the water molecules, but then you have the nonpolar chains, which are hydrophobic, and those interact with the oil particles, hence why we're able to dissolve some of those things and wash them away. So you can read up on that. It's just a cool application here. All right, so phase changes in energy. Phase changes, we know it takes energy to change us from a solid to a liquid and liquid to a gas. If we're looking at those things, the average kinetic energy of the particles cannot increase during a phase change because we have to break the intermolecular forces between our particles. So generally, if we think about this, a liquid is harder to vaporize or boil than a solid is to melt. And if you think about that, there are still relatively strong intermolecular forces between the liquid particles. So we only have to disrupt some of the intermolecular forces in the solid to turn it to a liquid. Whereas for turning something to a gas, we have to disrupt all of the intermolecular forces across the water molecules. We can also liquefy gases depending on their pressure and temperature. Again, this is an application of real gases. If we have a high temperature and a high pressure, we know that we can force the particles to interact with each other more. There are increased collisions, and when there are increased collisions, they have a chance to potentially form interactions with each other. So we have to get to a critical temperature, and we'll look at this in a phase change diagram in a bit. Critical temperature is the highest temperature at which a substance can remain a liquid regardless of the pressure applied, and the critical pressure is the pressure needed at that critical temperature. So this is really cool. Under certain conditions, things are no longer ideal, and they start to behave like real gases where they can form these intermolecular attractions. When they form the intermolecular attractions, they can then liquefy and go back to the liquid state. So as intermolecular attractions increase, the critical temp and the pressure can also increase. So some examples here, just comparing numbers. The critical temperature and pressure are rather large for ammonia. Let me right here, there you go. Ammonia and water are both rather large, and that's because both of these have hydrogen bonding in addition to their London dispersion forces. If we're looking at some of these other things, they don't necessarily have hydrogen bonding, but they do have dipole-dipole forces. Some don't even have dipole-dipole forces. Some only have London dispersion forces. You can see that the pressures are much lower for the things that only have London dispersion, like N2 and O2 and propane, which are all nonpolar. This leads us into our discussion of vapor pressure and the boiling of liquids. Some of the molecules on the surface of the liquid do have enough energy to escape the attraction of the liquid, and that can cause things to move in the gas phase. This is why things evaporate at room temperature. It's due to this vapor pressure. The vapor pressure is the pressure of the molecules above the surface colliding with the molecules at the surface. So as the number of molecules in the gas phase increase, the vapor pressure is said to increase, and when they strike the surface, they can return to the liquid. After some time, the pressure of the gas will be constant at the vapor pressure. This is said to be in equilibrium. So the point when as many molecules escape the surface as strike the surface is our dynamic equilibrium. That is our vapor pressure. So this is our pressure exerted when the liquid and vapor, like I said, are in dynamic equilibrium. So vapor pressure, the thing about vapor pressure is that it changes with temperature. We're looking at this graph here. Like I said, there's that correlation with temperature. Liquids boil when the external pressure equals the vapor pressure. So the atmospheric pressure has to equal the vapor pressure in order to boil. Typically for us, atmospheric pressure normally is at 1 atmosphere. So the vapor pressure has to equal 1 atmosphere for our liquid before it can boil. And so if we look at our graph here, water has a boiling point of 100 degrees, which means we have to get 100 degrees worth of energy into our water particles so that the vapor pressure will reach 760 millimeters of mercury or 1 atmosphere. For other liquids, they can boil at lower temperatures, and we actually have the ability to change vapor pressure depending on the external pressure as well. I'll talk about that in a minute. So a substance with a higher vapor pressure is said to be volatile. Higher vapor pressure readily evaporates. So diethyl ether, for example, here has a high vapor pressure normally at room temp, and so it evaporates a lot quicker than water would. So a substance with more intermolecular forces has a lower vapor pressure and therefore a higher boiling point. So that's the key thing to keep in mind. More IMFs means the particles stay in the liquid phase, they don't evaporate, so the vapor pressure is lower. And therefore, we have to put in more energy to get them up to that boiling point temperature where we're at equilibrium. So there are 2 ways we can get a liquid to boil. If we increase the temperature, that can get us to that equilibrium where our vapor pressure and our atmospheric pressure are equal. You can also look at the decrease of pressure. If you put water in a vacuum, you can actually boil it at room temperature if you decrease the pressure. If you decrease the pressure above the liquid, then that allows that equilibrium to be reached faster because more particles are escaping the surface to restore equilibrium. We're removing all of the air, and some of the particles have to escape the surface to balance that out, and as a result, we reach boiling at a lower temperature. Pressure cookers, for instance, operate at a high pressure. Since we have a high pressure, the boiling point of water is higher than 1 atmosphere, which means we have to get to a higher temperature. And so therefore, the food is cooked at higher temperatures, which reduces our cooking time. Boiling points increase with molecular weight as long as the intermolecular forces are similar. Again, that's a correlation, not an explanation. When we're looking at boiling points, you need to talk about polarizability. Molecular weight just means we have larger electron clouds. There's a larger mass, we have a corresponding number of electrons. Larger electron clouds are more polarizable, therefore stronger intermolecular forces. All right, so here's a phase diagram. In a phase diagram, it is a graph of pressure versus temperature, and it shows all of the phases. The critical temperature and critical pressure are at your critical point. Again, that's where we have that equilibrium where we can keep things a liquid or keep things a gas. Each phase boundary, those are your lines, each phase boundary represents an equilibrium set of pressure and temperature conditions. Use equilibrium in your explanations. Okay. Again, the critical point is the coordinate of your critical temperature and pressure. We also have what's called the triple point. This is a unique pressure and temperature where all 3 phases exist in equilibrium. And I actually have a short little triple point cell. Pull this out. And here you see all 3 phases. You've got the air bubble, which is your gas, you've got the liquid, and the crystals forming are your solid. Okay. So here are some phase diagrams comparing H2O and water. Notice that the pressures and the temperatures are very, very, very different, even though the graphs look fairly similar. And again, you have to think about the intermolecular forces occurring at each phase for each molecule. One of these is nonpolar, one of these is polar with hydrogen bonding, and as a result, that critical point and triple point are much different. So let's recap. With vapor pressure, if you increase your temperature, your vapor pressure will increase. As the molar mass of your substance increases, our electrons increase, therefore we're more polarizable, therefore we have stronger intermolecular forces, and therefore we decrease the escape of molecules and our vapor pressure goes down. The one exception, if we have hydrogen bonding in small molecules, that will decrease our vapor pressure as well. Because hydrogen bonding and the close proximity of those small molecules results in still strong intermolecular forces, even though we don't necessarily have large electron clouds. We could do calculations with this. If we were doing a lab, we could plot the natural log of our pressure versus 1 over our Kelvin temperature, and we get these nice linear trends. And we can use the slope to figure out delta H of vaporization here. It's called the Clausius-Clapeyron equation, but we're not going to really do any problems with that. If you're working on FRQs, you might see some problems that ask you to calculate vapor pressure. This is the equation you would use for those FRQs, but we wouldn't see that on the AP exam At least we haven't seen that since 2013, so you won't see that because of the redesign. Melting and freezing point. Just a reminder, I mentioned this earlier, temperatures remain constant during any phase change because the potential energy is changing, but the kinetic energy is constant. Melting and boiling point are therefore determined by your vapor pressure. Your vapor pressure of a solid is equal to the vapor pressure of a liquid at a melting point, and then the boiling point is the temp at which vapor pressure of your liquid equals the atmospheric pressure, which for us is 1 atmosphere. Some other things you might need to know if you're doing phase change calculations. Delta H of fusion is the enthalpy of fusion, which is the enthalpy, the amount of energy required to change from one state to another when you're at the melting point. So the plateaus, those are your flat line. You want to use Q equals delta H times the number of moles. If you're trying to figure out the slants, those are your increases. Use Q equals MC delta T. And here's just actually a better visualization of what's going on with phase changes and which equation type to use. All right, on to the solids. So the types of crystalline solids. We have ionic solids, molecular solids, and network atomic solids. The ionic solids are very high in melting point. They are hard. They have strong ion-ion Coulombic attraction, especially as we increase our separation of charge. So if I'm +1 and -1 compared to a +2 and -2, the greater separation of charge is a stronger attractive force, so the +2 -2 would result in a stronger lattice. With molecular solids, we have things that are covalently bonded molecules in the lattice, such as ice. They're strong bonding within the molecules, but they have weak intermolecular forces. And those are your London dispersion forces. Network atomic solids, these are things like carbon or silicon dioxide. So carbon has 3 different allotropes that we'll talk about. Diamond and graphite are 2 of them. These tend to be brittle. They don't conduct heat or electricity. We also have silicon dioxide, which I talked about as well, and that's found in both quartz, sand, and glass. When we're talking solids, I mentioned at the beginning amorphous and crystalline solids. Amorphous are kind of all over the place. There's no real rhyme or reason to their arrangement. Whereas things that are crystalline have a well-ordered, definite arrangement. And there's some examples there that you can read through. The different types of crystalline solids, we've got molecular, covalent network, ionic, and metallic. Molecular solids tend to be soft with low melting points and poor conductivity. If you've ever seen sulfur before, sulfur is yellow and it's relatively soft. That is a molecular solid. Covalent network solids is formed with the atoms. They're very hard with very high melting points and poor conductivity. We have ionic, which are the lattice. The lattice has a high melting point, poor conductivity, and can be very hard, but also brittle. So they're tough, but if you hit them in a certain way, they'll crack, and then they'll break apart that way. Metallic bonding is when metals bond with each other in a sea of electrons. That's why we have good conductivity, because there's that sea of free-flowing electrons. They are malleable, ductile, and they have high melting points. This is just recapping what I just mentioned about metallic bonding. And take a moment to read through that chart. And here are just some graphics here. So diamond and graphite are both carbon allotropes. I'll talk about that in a moment. The graphite forms these nice little sheets that kind of stack on top of each other, where diamond forms these interlocking hexagonal arrangement of, or actually it's tetrahedral arrangement of carbon atoms. This is a good representation of your metallic bonding. You've got these positive cores with electrons that kind of flow all in between here, every which way, electrons going all over the place. It's a sea of electrons. And then here we've got our lattice. There are a couple of different types of lattices, but you don't need to know the names of the specific ones. Again, the 3 different allotropes. We've got graphite, diamond, and then buckyballs, which are really interesting. I recommend Googling buckyball and just reading up on them. Silicon is a covalent network solid. It's also a semiconductor. What's cool is the arrangement determines what you've got. So sand is just a bunch of particles of silicon dioxide, whereas if you're looking at glass, it's the amorphous version of silicon dioxide, where the arrangement's kind of all over the place. And then if you look at quartz, it's got a definite structure to it. But this is an example of a network solid. We also have alloys. Metallic solids are often pure substances, but we can also make mixtures called alloys. We have interstitial alloys where we are able to put smaller atoms in between the spaces of the larger atoms. So steel would be a good example there. And then we also have substitutional alloys like brass, where we stick the atoms of one metal in between atoms of the other metal. So they just end up alternating rather than being kind of shoved in between the atoms in the spaces. And you can read through each of those things momentarily. And that's actually all I've got for you today. I know this one ran a little long, so I'm going to try and trim it down. Have a great day.